Now we have our next speaker, Byeongjee Kang, who is a PhD student at Carnegie Mellon.
Thank you for the introduction. I'm Byeongjee, and I'm a PhD student at Carnegie Mellon, and today I'm going to talk about my ongoing research on MLIR Dialect for WebAssembly, which is a joint work with my collaborators Harsh, Brandon, and my advisor Limin. So to give you some background, we have been working on a pipeline to compile and deploy programs on multiple platforms. The source program could be some machine learning application or some general program written in a high-level language, and the target platform could be, So the target platform could be a web browser, desktop computer, or microcontrollers, and etc. And we know that WebAssembly is a great fit for this use case. It offers us several benefits, and importantly, it offers us great portability for our use case. So once we compile high-level programs into Wasm, we can deploy them anywhere. And among those target platforms, we are particularly interested in microcontrollers for now because they impose interesting challenges. So different microcontrollers have different memory requirements and different hardware abstractions and resource constraints. So programming on microcontrollers means that we have to deal with low-level details of microcontroller, and this is very difficult to do correctly and efficiently if you don't have the expertise. But thankfully, Wasm can be a good solution for this. It offers us abstraction to decouple device-specific details from Wasm code. This means that if we have a good Wasm runtime, for example, Wasm micro runtime for microcontrollers that is built by expert on microcontrollers, then we can just let the runtime do all device-specific details or optimizations, and the application developers can just focus on compiling their code into Wasm without thinking about the underlying architecture. And also, we want to mention that high-level Wasm features provide even more opportunities in this case. For example, suppose that we have a Wasm garbage collection feature. We can use these to abstract away details of memory allocation strategies from user-level code to runtime implementation. So even if we have the same Wasm code, we can use different memory allocation strategies in different microcontrollers based on the memory sizes in devices and etc. Now the problem is that we want to compile these high-level programs into Wasm. So the program could be a machine learning application or some microcontroller-specific application written in some high-level domain-specific language, or it could be some general program. And our goal would be to compile this into WebAssembly. So we need to build a compiler in some sense. And because we don't want to build a new compiler from scratch, we wanted to use a reusable compiler infrastructure like LLVM. And after that, we decided to use MLIR compiler infrastructure for our use case. It's a recently developed framework that is maintained by the LLVM community. It offers great modularity and extensibility. So let me briefly explain how MLIR works. So this is an example, simplified figure showing that how high-level ML program can be compiled into WebAssembly. So each box in the diagram is called a dialect, which is an abstraction layer in MLIR. It is a collection of operations and types that could be used to represent some concept. And MLIR program has operations in one or more dialects. And the compilation is done by a series of dialect conversion passes, which is shown as arrows here, which converts high-level dialects into lower-level dialects progressively. So for example, there is a TOSA dialect, which stands for Tensor Operator Set Architecture. And it has operations like TOSA.constant, which defines constant tensor, and applying convolution operation on them. And after a series of dialect conversion passes, we can actually convert this into lower-level dialect, which is Linak dialect. It has operations like matrix multiplication and etc. And after applying more dialect conversion passes, we can actually convert this into, for example, SCF and RS dialect, where SCF stands for structured control flow, and it has operations like for loops. And RS is a dialect for arithmetic operations like multiplication and addition on color. And we can even convert this into CF dialect, which is unstructured control flow, which has operations like branch to label and etc. And after we get into this low-level MLIR dialect, we can finally convert them into LLVM and use existing LLVM backend to convert this into WebAssembly. So this seems good so far, but there is one problem. The problem is that existing compiler infrastructure, including MLIR and LLVM, they choose to convert the high-level programming into some shared abstraction, for example, LLVM, to make their compiler reusable. And this shared abstraction are often designed with conventional assembly targets, like conventional compilation targets like x86 and ARM in mind. So they have abstraction level that is similar or slightly higher than them. So this works perfectly fine for them, but there is a problem when it comes to WebAssembly. WebAssembly has features that are higher level than conventional assembly formats. So for example, it has instructions to define garbage collected data types and structs, and it can have like multiple memory spaces, and even like the stack switching feature will provide us a way to define continuations and switch between them as Wasm instruction level. So while these kind of features may have existed in the high-level program, the existing compiler infrastructures actually de-abstract this concept into some shared abstraction. And from that shared abstraction, it is difficult to take advantage of these high-level Wasm features and use them effectively. So the problem statement can be summarized into one sentence. Existing compiler infrastructures do not support compiling to Wasm with high-level features in a reusable and extensible way. So in this talk, we will propose a new MLIR-based compilation pipeline that solves this problem. So this is the outline of the remaining of the talk, and I will start with a motivating example first. So first, as a motivating example, I will explain about the intermittent computing, which is an important class of application in microcontroller programming. So the goal here is to run programs on small microcontrollers that doesn't have any battery or power cord. So how these devices work is that they accumulate energy from external environment, for example, from sunlight, and store the energy into some capacitor. And once enough energy is accumulated, it goes through execution phase, which lasts typically for a few milliseconds, and the program runs for that time. And after that, the energy runs out, and the microcontroller experiences power failure, and we go through charging and execution phase again and again. The problem here is that when it experiences power failure, the microcontroller loses all its volatile state. So we have to find a way to make sure that the program state is not corrupted. Program state, which consists of both non-volatile and volatile memory states, is not corrupted during frequent power failures. And there are several researches that have been done to overcome this issue, and I'm going to introduce one, which is called Alpaca programming model. This is a programming model for microcontrollers for intermittent computing, which uses some concept of task and transition between tasks. So you can think task as a granularity of atomic execution, and transition to statement as a operation that saves some context and switches to another task. We have also built a domain-specific language for this intermittent computing with some task and transition to operations. So now the problem is that we want to compile this into WebAssembly. And ideally, this transition to statement should be compiled to some form of context switching. But the problem is that context switching on microcontrollers is very difficult to implement well. We may have to think about whether to enable or disable certain interrupts and traps during context switching, and we also have to think about whether to store the switched out context in certain memory regions, because like different memory regions in microcontrollers have different access latency, so we have to optimize this somehow. So this is very microcontroller specific thing and difficult to implement, but there is one solution that we can think of, which is using a stack switching proposal. This proposal provides instructions to define and define continuations and switches between them. And I think like this will be covered later in this workshop. But from our perspective, this is great because we can use this to abstract away details of context switching from Wasm code. So the runtime implementation which can be done by each microcontroller experts, can take advantage of like this microcontroller specific optimizations during context switching. And also there are more high-level Wasm features that could be helpful to abstract away device-specific details from Wasm code. For example, there could be multiple memories, garbage collection, exception handling, and etc. And more importantly, there will be more of such features in the future as Wasm is an evolving language, unlike other hardware-level assembly formats. Now I'm going to talk about problems with existing compilers, or why it is difficult to generate such high-level Wasm features from existing compilers. First, there are compilers, some languages like Go, Lang, and Haskell chooses to build their own compilation pipeline for WebAssembly and other assembly formats. This approach is definitely flexible, but this is not reusable. We need duplicate work for each source and target language. And also there is one Wasm-specific complexity, which is that Wasm itself is evolving. So if we build a custom compiler, the developer is responsible for updating the compiler by themselves as the Wasm features are being added. And also, next let's talk about the reusable compiler infrastructures. So the most popular reusable compiler infrastructure is LLVM, which is used by C, C++, and Rust. But as it goes through a shared abstraction layer called LLVM, it experiences abstraction loss, as we explained earlier. Then, what can we do about this? The first option could be re-abstract high-level concepts from low-level abstraction. And this is actually an attempt that is done by Amscripten, which is LLVM to Wasm compiler. Since Wasm, unlike LLVM, which allows arbitrary form of jumps to labels, Wasm only supports some certain form of structured labels for security and simplicity reasons. And because of that, the Amscripten developers had to build a control flow transformation passes to convert control flows in LLVM into WebAssembly compatible ones. They did it through a non-trivial algorithm called relooper, but in general, there is no guarantee that such kind of re-abstraction is doable. In general, re-abstraction is hard. And another thing that we can think of is to extend LLVM to preserve the high-level information through the compilation pipeline. But this is also difficult because LLVM is not meant to be extended in some sense. It offers some form of extensibility, but in general, adding a new instruction or adding a new type will bring compatibility issues into LLVM, and it is difficult to use this update LLVM frequently to keep up to date with Wasm changes. Then, how about existing MLIR to Wasm pipelines? So as I mentioned earlier, MLIR has multiple levels of abstraction, and it is designed to be easily extensible, so it has some advantages over LLVM. But fundamentally, we still lose abstraction in this pipeline because what we are doing here is to compiling the MLIR dialects into LLVM and rely on LLVM backend to generate Wasm. So our idea is to get rid of this LLVM from the compilation pipeline and keep the abstraction as much as we want. So let's get back to this diagram showing the example of compilation pipeline from high-level ML applications to WebAssembly. What we do here is, instead of using LLVM, we introduce a new dialect in MLIR world called MLIR Wasm dialect. This dialect has a one-to-one correspondence with WebAssembly, so it can be directly translated into Wasm. So now the compilation to Wasm can be done through dialect conversion passes that converts existing MLIR dialects into the Wasm dialect. So for example, we can build dialect conversion passes from low-level memref and RS dialect into Wasm dialect, which is straightforward. And another benefit is that we can choose which dialect we want to convert from. For example, instead of generating like Wasm dialect from CF or unstructured control flow dialect, we can actually generate Wasm from SCF, structured control flow dialect. So the advantage of doing this is that in this case, this translation is trivial, almost trivial. We don't need to think about re-abstraction algorithm like relooper as LLVM did. And another benefit is like, let me talk about an example of tensor and MLIR dialect first. So tensor dialect here is a dialect for high-level immutable data type for tensors, and MLIR and we can actually convert this into lower-level dialect, which is MLIR dialect, and it has operations related to memory allocation, access, free deallocation, and etc. What we're doing previously was to convert this MLIR dialect into LLVM and to WebAssembly. But actually, we can actually think of converting tensor dialect directly into Wasm dialect. For example, using Wasm GC features, using the arrays, types, and structs type that are provided by Wasm. In this sense, we can take advantage of high-level Wasm features. And for example, if you have a high-level language, if you have implemented a high-level language, what you can do to compile this MLIR into we can actually compile this into MLIR Wasm dialect before like losing its abstraction. So in that case, we can use high-level features of Wasm. So I'll give you a case study, intermittent computing language as an example. So we have built a domain-specific language for intermittent computing, and in order to compile this through MLIR pipeline, we have developed an MLIR dialect that mirrors this domain-specific language. So our goal is to compile this into WebAssembly. And actually, this is doable, even without Wasm dialect. But without Wasm dialect, what we can do is to convert them into LLVM with complex coroutine-related intrinsics and rely on complex compiler transformation passes that inserts the context switching code to user level. So for example, we have to include malloc, which is responsible for allocating frame to store the context, and we have to do store and save and restore context at user code level. So in that case, the binary size will be bigger, and we cannot take advantage of any device-specific optimizations. However, if you go through Wasm dialect, the transition to statement can be actually simply converted into single switch statement in the stack switching proposal, which performs some kind of context switching. And through this, we can actually get smaller binary size, and we also have to bundle the malloc code for this. And also, we have room for more optimizations. We can rely on runtime implementation optimizations that utilize the domain-specific information, device-specific information. And also, I want to mention that once we build a dialect conversion path from some dialect to Wasm, we can actually, all the high-level languages and dialects can reuse these conversion paths. So this is a reusable compilation pipeline. And now I'm going to briefly mention our ongoing work on performance evaluation. So as we haven't implemented any optimization on our compilation pipeline yet, this is obviously much more slower, which is expected. But actually, for our use case, we are focusing on compiling WebAssembly ahead of time to binary machine code and also apply binary optimization before that. And in this case, it turns out the performance is quite comparable. There are some points where the performance of my compiler, where the code produced by my compiler is somewhat slower than LLVM, but there are also cases where my compiler actually produces faster code, which is interesting result, considering that I haven't implemented any optimization in my compilation pipeline yet. We are still figuring out what is exactly happening here.
Can you speak to a little bit more of what's in your benchmarks? Just by the names, they seem like they're doing more long integers, vector operations.
Yeah, so it's mainly related. It's actually a benchmark suite for polyhedral optimization, for testing polyhedral optimizations, and I chose this because it has MLIR port of it, and it mainly has like benchmark suite related to like matrix multiplication and dealing with arrays and etc. So it is mainly for like tensor operations, and we have tested this on microcontrollers. So I'm going to finish the talk with possible future works. So first, I think I can use this MLIR Wasm dialect to support other Wasm features. For example, early phase Wasm features that don't have much users yet. I think we can use this MLIR Wasm dialect to create or get more users or high-level languages that compiles to them. And also, as we don't use LLVM anymore, I think this is a great opportunity to perform end-to-end compiler verification or analysis research. So, because LLVM is a so large project, it works as some kind of black box for if you want to perform some end-to-end verification. But as the compilation pipeline is now much simpler and can be customized more easily, I think we can also do research on this direction as well. So this is all of our talk, and I'm happy to take any questions.
Thanks, that's great. Just before I open it up to the floor, I have a couple of questions. Since Sam is in the room, I won't ask the stack switching question. But I was interested, I didn't realize MLIR had so many different dialects. Did you ever find that there was some tension in designing the Wasm dialect between reusing the existing dialects, so you're not having to come up with a lot of your code, and at the same time, adding all these WebAssembly specific things? Were there any design decisions you might want to revisit or iterate on later?
I think there actually are a lot of things. So first, like Wasm is a stack-based assembly format, while like MLR is originally a assembly originally format for SSA forms, which has like variable declarations and etc. So we have to handle that conflicts in that somehow. And also, Wasm has some operations like block, which, so if you branch to a block, it branches to the end of the block, but not the beginning of that. And like MLIR doesn't have like such notion of control flow, so it brings, it also has some issues there. So we need to fix that. And also we are going to refactor our pipeline to have add more like intermediate dialects, but that's, yeah.
That's very gratifying to see you making use of the stack switching extension. I'm curious, have you actually tried running that code? Because there's only really an experimental implementation so far in Wasm time. Have you?
So yes, we are trying to running it on WasmFX time. Are you a developer of that?
He's the main proposer.
Oh, yes.
I'm the champion of the proposal.
Actually,
one of the co-champions.
I remember that I've created a GitHub issue on the WasmFX time that like I needed some stack switching feature.
Ah, right.
Yeah, that's like what we were looking for.
Oh, cool. So you've actually tried running the benchmarks.
And we are also trying to running that on microcontrollers by porting them on WAMR runtime.
Excellent. Great.
You two should definitely talk to each
Yeah, sure.
Hi, so this is more of a clarifying question, I suppose. Like, you did not only define a Wasm MLIR dialect, you also wrote a compiler from the Wasm MLIR dialect straight to Wasm. And you're skipping like the LLVM part entirely?
Yes, I'm skipping that entirely. And the goal of designing the Wasm dialect, the design decision of like making the Wasm dialect is to make it as similar as the Wasm itself. So the translation from the MLIR Wasm dialect to Wasm can be done trivially, just by the one-to-one translation.
Okay, thank you.
I'm curious what microcontrollers you're running, just in terms of, especially because I know that a lot of microcontroller programming happens in C, and LLVM should be able to deal with that fairly well.
For now, we are running it on Apollo 4 device, which has like Cortex-M4 CPU.
Okay. The other question was, are there any WASM to WASM optimizations that MLIR can do better than maybe binarian or the current LLVMIR in your experience?
I think there could be, because but I don't have a clear answer for that. We're still looking into the issue. Maybe I think by looking into this performance, sorry, I don't have the slides, but by looking into the performance gap in our benchmarks, I think we can try figure it out.